Part 1. The universe is running away from itself. There is something happening right now that you cannot see, cannot feel, and cannot stop. Every galaxy you have ever seen photographed, every deep field image with its thousands of smeared lights pressed against the dark, every glowing spiral and elliptical cloud of ancient stars, all of them are moving away from you. Not because they were pushed, not because something exploded and sent them scattering, but because the space between you and them, the actual fabric of reality that separates one point in the cosmos from another, is growing, stretching, swelling outward in every direction simultaneously, like the surface of a balloon being inflated from within, except the balloon has no edge, no center, and no one holding the nozzle. This is not a metaphor. This is the physical condition of the universe you live in right now, tonight, in whatever quiet corner of the world you are watching from. The space between the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor at roughly 2.5 million light-years away, is not currently growing because we are on a collision course with each other and their gravitational pull has temporarily reversed the trend. But every galaxy beyond the local group, the handful of galaxies bound together by gravity in our immediate cosmic neighborhood, is receding from us at a speed proportional to how far away it already is. The farther the galaxy, the faster it moves. Not because distant galaxies are running harder than nearby ones, but because there is simply more space between us and them that is expanding, and every unit of that expanding space adds its contribution to the total recession speed. This is Hubble's law, and it is one of the most elegantly strange relationships in all of science. To understand how we arrived here, you need to go back to a mountaintop in Southern California in the late 1920s, to a man named Edwin Hubble standing at the eyepiece of the largest telescope in the world, the 100-inch Hooker reflector at Mount Wilson Observatory. Hubble had already done something remarkable by the middle of that decade. He had looked at fuzzy patches of light called spiral nebulae that most astronomers assumed were clouds of gas within our own galaxy, and shown, by measuring the distance to Cepheid variable stars embedded within them, that they were far, far outside the Milky Way. They were entire separate galaxies, island universes scattered through a space that was vastly larger than anyone had imagined. What had been thought to be the entire universe turned out to be just one neighborhood in an incomprehensibly vast cosmic city. But Hubble was not done. What he turned to next was a property of the light coming from these galaxies that had already been measured by his colleague Vesto Slipher over the preceding decade. The light from most of these galaxies was redshifted. Its wavelength was stretched toward the red end of the spectrum, the way an ambulance siren drops in pitch as it drives away from you. And in 1929, working with his assistant Milton Humason to extend the measurements to fainter and more distant galaxies, Hubble noticed the relationship that would change everything. The more distant a galaxy was, the more its light was redshifted. The more its light was redshifted, the faster it appeared to be receding. Distance and recession speed were proportional to each other, connected by a constant, now called the Hubble constant, that told you how fast a galaxy at any given distance was moving away. Plot the recession speeds against the distances, and the points fell along a straight line. A simple, clean relationship between where something was and how fast it appeared to be moving away. When Hubble published his data in March 1929, the scientific community did not immediately understand what they were looking at. The paper was interesting. It showed a relationship, but it did not cause the kind of immediate uproar you might expect from the discovery that the entire observable universe was in motion. The implications took time to settle in, partly because Hubble himself was cautious about interpretation, and partly because the reigning picture of the cosmos, a static, eternal universe that simply existed without origin or end, was so deeply embedded in the assumptions of the time that most people were not yet ready to reach for what the data actually implied. Albert Einstein had been there first, in theory if not in observation. When he developed general relativity in 1915 and applied his equations to the universe as a whole, the mathematics told him clearly that a universe filled with matter could not sit still. It would either expand or contract. Einstein found this so disturbing, so philosophically unacceptable, that he inserted an additional term into his equations, a constant he called the cosmological constant, chosen specifically to counteract the gravitational tendency and hold the universe in steady balance. When Hubble's observations were brought to his attention, Einstein reportedly called the introduction of the cosmological constant his greatest blunder. The universe was not static. It had been expanding all along, and his equations had known it before his intuition was willing to accept it. What Hubble's law describes is not galaxies moving through space the way a rocket moves through the air. The galaxies themselves are, in most cases, not shooting outward from some central explosion point. What is expanding is the space between them. This is a distinction that matters enormously because it removes the speed limit you might otherwise expect to apply. Special relativity says that nothing can move through space faster than light, but space itself has no such restriction. Space can expand at any rate, and the consequence of that unrestricted expansion is that galaxies far enough away from us are already receding at speeds exceeding the speed of light. Not because they are moving fast through space, but because the volume of space between us and them is growing at a rate whose implied velocity at that distance exceeds light speed. Right now, galaxies at distances beyond roughly 14 billion light-years are receding from us faster than light. We can still see some of them because the light they emitted long ago, when they were closer, has had time to reach us. But any light they are emitting today will never reach us. The space between us and them is growing faster than light can cross it. Those galaxies are, for all practical purposes of observation and communication, already gone. And this is the thing that should make you stop and sit with the strangeness of where you are in time. We happen to live in an epoch where the universe is observable, where billions of galaxies are visible to our instruments, their ancient light still reaching us across distances that strain the imagination. But the universe is not staying this way. The expansion is not merely continuing, it is accelerating. The galaxies are not just receding, they are receding faster and faster with every passing age. And if that continues, the observable universe will shrink. The skies will empty. The distant galaxies will redshift beyond detection. Their light stretched to wavelengths too long and too faint for any instrument to register. And eventually the Milky Way and its gravitationally bound neighbors will sit alone in an expanding dark. The rest of the universe, not merely invisible, but forever unreachable and unknowable. We are watching the universe before it goes dark. But here is the question that sits at the heart of everything we are about to explore together. Is this the final story? Will the expansion continue accelerating forever, stretching space into an infinite cold void? Will it slow, stall, and reverse, collapsing everything back into a singularity of unimaginable density? Will it tear itself apart with increasing violence, shredding galaxies and stars and atoms in a final cataclysm? Or will it simply coast to an asymptotic stillness, expanding forever but slower and slower, approaching some terminal state but never quite reaching it? To answer those questions, you first need to understand what is driving the expansion in the first place. And the honest answer, as you are about to find out, is that we do not entirely know. But we know enough to map the possibilities. And the possibilities range from quietly haunting to spectacularly violent, in ways that genuine physics can describe with precision, even if the outcome still hangs on a number we have not yet pinned down. Let us start with how we found out that the expansion was not just continuing, but speeding up. A discovery so unexpected that the people who made it took years to fully believe their own data. Before continuing, drop a comment and let us know where in the world you are watching this from and what time it is there. And if you have not subscribed yet, now is a great moment to do that. There is a lot more of this journey ahead, and you do not want to miss where it goes. Part 2. How we learned it was not slowing down. For most of the 20th century, astronomers assumed that while the universe was expanding, it must be slowing down. This seemed obvious, almost trivially so. Gravity pulls. Everything in the universe exerts a gravitational attraction on everything else. The Big Bang had set matter flying outward in every direction, and gravity was the braking force, gradually tugging on all that outward moving material, reducing the expansion rate over time. The universe might expand forever if it had enough initial energy to overcome gravity's pull, or it might slow, stop, and reverse, eventually collapsing back on itself in what cosmologists called the Big Crunch. But in either scenario, the expansion rate should be declining. That was the unavoidable implication of a universe where matter existed and gravity was real. The question for observational cosmology in the latter half of the 20th century was not whether the expansion was decelerating, but by how much. Get the deceleration rate precisely enough, and you could predict whether the universe would expand forever or eventually reverse. The answer hinged on a comparison between the expansion rate and the density of matter and energy in the universe. Above a certain critical density, gravity wins eventually, and the universe collapses. Below it, expansion wins indefinitely. Right at that critical density, the universe expands forever, but asymptotically, slowing toward zero speed, but never quite reversing. To measure the deceleration, you need a way to compare the expansion rate of the universe in the distant past with the expansion rate today. And the tool that made this comparison possible was a particular type of exploding star called a Type Ia supernova. When a white dwarf star in a binary system accumulates enough mass from its companion to push past a critical threshold of roughly 1.4 solar masses, a threshold known as the Chandrasekhar limit after the astrophysicist Subrahmanyan Chandrasekhar, who calculated it in the 1930s, carbon fusion ignites throughout the star almost simultaneously. The result is a thermonuclear explosion so powerful it outshines entire galaxies for weeks. What makes Type Ia supernovae cosmologically useful is their consistency. Because the triggering mechanism always occurs at the same mass threshold, these explosions always release approximately the same amount of energy, always reach approximately the same peak brightness. They are, in the language of cosmology, standard candles, objects whose intrinsic luminosity is known, so that by measuring how bright they appear from Earth, you can calculate how far away they are. In the mid-1990s, two teams of astronomers independently embarked on programs to measure the deceleration of the universe using Type I supernovae. One team, the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other, the High Z Supernova Search Team, was led by Brian Schmidt at the Australian National University, with Adam Rees playing a critical role in the data analysis. Both teams were searching for distant supernovae, measuring their brightness and their redshift, and comparing their apparent luminosity to what it should be if the universe had been decelerating at various rates. The expectation was that distant supernovae, seen as they appeared billions of years ago when the universe was younger and the expansion rate was therefore higher, would appear slightly brighter than a non-decelerating universe would predict. The universe would have been expanding faster in the past, meaning those ancient supernovae were slightly closer to us at the time of explosion than a constant expansion would imply, meaning their light would be slightly more concentrated when it reached us. What both teams found when their data came in was not what they expected, at all. The distant supernovae were dimmer than expected, not brighter. They appeared to be farther away than a decelerating universe would place them. The expansion was not slowing down. It was speeding up. The universe was not breaking. It was accelerating. Both teams found the same result independently. Both teams checked their work obsessively. Both teams suspected systematic errors. Dust in the line of sight could make supernovae appear dimmer than they were. Possible differences between ancient and modern supernovae could introduce biases. Evolution of the white dwarfs over cosmic time could shift the calibration. One by one, the potential explanations were examined and ruled out. The result held. The results were published in 1998 and 1999, named by the journal Science as the breakthrough of the year in 1998, and eventually honored with the Nobel Prize in Physics in 2011, awarded jointly to Perlmutter, Schmidt, and Rees. The universe was not just expanding, its expansion was accelerating. Something was pushing space apart against the pull of gravity, something pervasive, filling all of space, exerting a repulsive influence that grew stronger as the universe grew larger, overwhelming gravity on the largest cosmic scales, and driving galaxies apart at an ever-increasing rate. Nobody had any idea what this something was. The immediate response from cosmologists was to reach back to Einstein's discarded cosmological constant, the term he had introduced to hold the universe static, and then abandoned when Hubble's observations showed the universe was expanding, turned out to be precisely what the data demanded. A cosmological constant in Einstein's equations acts exactly like a uniform energy density filling all of space, exerting negative pressure, driving expansion to accelerate. The value needed to match the supernova observations was tiny, unimaginably small, but non-zero, and it was consistent with all the other cosmological data: the temperature fluctuations in the cosmic microwave background, the distribution of galaxies on large scales, the estimates of the universe's total energy content. The picture that emerged was striking. The universe, it turned out, is not primarily made of the atoms and molecules we think of as matter. Ordinary baryonic matter, the protons and neutrons and electrons that make up stars and planets and people, accounts for only about 5% of the universe's total energy content. About 27% is dark matter, a form of matter that does not interact with light and whose nature remains genuinely unknown despite decades of searching. And the remaining 68%, the majority, the dominant component by far, is this mysterious dark energy, filling space uniformly, driving the accelerating expansion, responsible for the cosmic behavior we are trying to understand. Dark energy is the engine of cosmic expansion, and we do not know what it is. We can measure its effects. We can quantify its influence on the expansion history of the universe. We can constrain its mathematical properties to remarkable precision. But the physical nature of whatever is filling space and pushing it apart, whether it is the energy of the vacuum itself, or a dynamic field slowly rolling through some potential, or something altogether different that requires new physics we have not yet imagined, remains genuinely, profoundly unknown. The discovery of accelerating expansion was not just a measurement of a number, it was a signal that the standard picture of the universe was fundamentally incomplete. The cosmos contains a dominant ingredient we cannot identify, cannot directly detect, and cannot predict from our existing theoretical understanding. The expansion we are trying to trace to its ultimate conclusion depends entirely on the behavior of this ingredient over cosmic timescales, and that behavior is what the most ambitious astronomical projects of our current era are racing to characterize. The 1998 discovery changed the question from, will the universe expand forever or collapse, to something far more open. What is dark energy? How does it behave over time? And what does that behavior imply for the ultimate fate of everything that exists? These are not questions with comfortable answers, but they are questions that genuine observational physics is actively pursuing, and the answers that are beginning to emerge in the mid-2020s are more surprising than almost anyone anticipated. Part 3. The Hubble Tension, a universe that will not give a single answer. Before we arrive at the most recent and most unsettling findings, there is a problem that needs to be laid out, because it suggests that our understanding of cosmic expansion is incomplete in a way that goes beyond merely not knowing what dark energy is. There is a disagreement within cosmology so persistent, so well tested, and so stubbornly resistant to resolution that it has earned its own name, the Hubble tension, and it points either to a systematic error somewhere in our most careful measurements, or to new physics that the standard model of cosmology simply does not contain. The Hubble constant, that number relating distance to recession speed, is the single most important quantity for understanding the expansion of the universe. Measure it precisely, and you have the current expansion rate, a key input into every model of cosmic evolution past and future. You can determine the age of the universe from it. You can constrain the history of expansion and therefore the behavior of dark energy. You can predict the ultimate fate of the cosmos. Getting this number right is not an academic refinement. It is the foundation. The problem is that two fundamentally different methods of measuring the Hubble constant give two different answers, and they do not agree within their stated uncertainties. The first method looks at the early universe. The cosmic microwave background radiation, the afterglow of the hot, dense phase of the early universe that was released when the universe cooled enough for electrons to combine with protons and light to travel freely, about 380,000 years after the Big Bang, carries within it a precise snapshot of the universe's conditions at that moment. By mapping the tiny temperature fluctuations in this background radiation with instruments like the Planck satellite, cosmologists can determine the composition and geometry of the early universe with extraordinary precision. Then, using the standard cosmological model, they run those early universe conditions forward in time to predict what the Hubble constant should be today. The Planck collaboration has done this calculation with great care and consistency, arriving at a value of approximately 67.4 kilometers per second per megaparsec. For every megaparsec of distance, roughly 3.26 million light-years, a galaxy recedes from us at 67.4 kilometers per second. The second method looks at the late universe directly. Astronomers measure distances to nearby objects using Cepheid variable stars, whose pulsation period is directly related to their intrinsic luminosity, allowing precise distance determinations. They then use those Cepheid-calibrated distances to anchor the distance ladder at closer distances, then extend the ladder outward using Type 1a supernovae visible to much greater distances, and finally measure the recession speeds of those distant supernovae to determine the current expansion rate directly. The SH0ES team, led by Adam Rees and using data from both the Hubble Space Telescope and the James Webb Space Telescope, has performed this measurement with extraordinary precision and consistently finds a Hubble constant of approximately 73 kilometers per second per megaparsec. The difference between 67.4 and 73 sounds small. It is not. Those measurements carry uncertainties of about 1%. The discrepancy between them is roughly 5 times larger than either measurement's uncertainty, a disagreement that in the language of statistics reaches the level of 5 sigma, which is the threshold conventionally used to declare a new physics discovery in particle physics. A 5 sigma disagreement means there is less than roughly a 1 in a million chance that the two measurements are actually compatible and the difference is just a statistical fluctuation. The disagreement has persisted for over a decade. It has survived improvements in the Cepheid calibration. It has survived the transition from the Hubble Space Telescope to the James Webb Space Telescope for distance measurements. It has survived multiple independent checks using different types of standard candles, different calibration methods, different analysis approaches. The Webb telescope's superior resolution and sensitivity were expected by some to reveal that Hubble's Cepheid measurements were contaminated by crowded stellar fields, blending multiple stars together and biasing the brightness measurements. But the Webb measurements confirmed the Hubble results. The discrepancy remained. What does a 5 sigma disagreement between two precise, carefully vetted measurements of the same quantity actually mean for physics? There are two possible explanations. Either there is a systematic error in one or both measurement methods that nobody has yet identified, some subtle bias that makes one method consistently overestimate or underestimate the true value. Or the universe does not behave the way the standard cosmological model assumes between the early universe epoch, probed by the cosmic microwave background, and the late universe epoch, probed by the distance ladder, meaning something happened in the intervening 13 billion years that our model does not capture. The second possibility is the more exciting and the more alarming. If the Hubble tension reflects new physics rather than a measurement error, it means our current cosmological model is wrong in some important way. Dark energy might behave differently over cosmic time than a simple constant implies. There might be additional light particle species in the early universe that we have not accounted for. There might be interactions between dark matter and dark energy. There might be modifications to the behavior of gravity on cosmological scales. All of these have been proposed as possible resolutions to the tension, and none has yet achieved consensus among cosmologists. The Dark Energy Spectroscopic Instrument, installed on the Mayall telescope at Kitt Peak Observatory in Arizona, maps millions of galaxies by measuring the spectrum of their light, charting the distribution of galaxies across the universe, and using that distribution to trace the expansion history. DESI's 2024 and 2025 results largely aligned with the lower Planck value of the Hubble constant from early universe probes, adding to the weight of evidence that the two camps of measurements are genuinely in disagreement rather than converging on a middle ground. The Hubble tension is not resolved. It remains one of the most actively debated problems in observational cosmology, and its resolution, whenever it comes, will either reveal a subtle flaw in our most careful observational work, or announce that the standard model of the universe needs to be replaced by something richer, something that encompasses new physics we have not yet written down. Either outcome tells you something important about where we stand. Our best current tools are in genuine disagreement about the current rate at which the universe is expanding. That fact alone should impress upon you just how genuinely open these questions remain, how much of the story of cosmic expansion is still being written, in real time, by real scientists with real telescopes pointed at a universe that keeps producing surprises. Part 4. Dark Energy, the Force We Cannot Name. Of all the strange things physics has uncovered about the universe, quantum tunneling, black hole singularities, the wave-particle duality of matter, the fact that time runs slower near massive objects, the cosmological constant problem might be the strangest. Not because the problem is conceptually difficult in the way that quantum mechanics is difficult, requiring you to let go of classical intuitions, but because the problem is quantitative. There is a specific number that theory predicts and a specific number that observation measures, and the gap between those two numbers is 120 orders of magnitude. 120 orders of magnitude. Written out, that is the number 1 followed by 120 zeros. If the theoretical prediction were a skyscraper of ordinary height, the observed value would be a single atom sitting on the floor of that building. That is the scale of the discrepancy between what our best theories of quantum field theory tell us dark energy should be and what it actually appears to be. Here is where the problem comes from. In quantum field theory, empty space is not truly empty. The vacuum is filled with quantum fields, and those fields fluctuate. Virtual particles pop in and out of existence at every point in space, and those fluctuations carry energy. The vacuum has energy. Quantum field theory lets you calculate how much vacuum energy to expect, and the answer, depending on which energy scale you cut the calculation off at, comes out somewhere between 10 to the 55th power and 10 to the 123rd power, times larger than the observed dark energy density. If the vacuum energy were as large as quantum field theory predicts, the universe would have expanded so rapidly and catastrophically in its first instant that no galaxies, no stars, no atoms, and no observers would have ever had time to form. The cosmos would have flown apart before complexity had a chance to assemble itself. The observed dark energy density is extraordinarily small, not zero, which would at least be explainable as a cancellation enforced by some as yet unknown symmetry, but small in a way that requires some mechanism to reduce the theoretical value by anywhere from 55 to 123 orders of magnitude, and then leave a precise, tiny residual. No known physical mechanism achieves this. No symmetry principle predicts this residual. This is the cosmological constant problem, and it is widely regarded as the deepest unsolved problem in theoretical physics. The simplest interpretation of dark energy is that it is exactly this cosmological constant, a fixed property of space itself, an energy density that does not dilute as the universe expands, does not change over time, and exerts a constant repulsive pressure throughout all of space at all times. In this picture, the dark energy density is a constant of nature, as fundamental and unchangeable as the speed of light or the mass of the electron. And if that is true, the expansion of the universe will continue to accelerate indefinitely, forever. The universe will expand at an ever-increasing rate, and that rate will never reverse, never slow to zero, never allow gravity to reassert dominance on the largest scales. This is the cosmological scenario called the Big Freeze, and we will explore it in detail shortly. But the cosmological constant is not the only possibility. There is a rich theoretical landscape of alternative dark energy models, unified under the general label of dynamical dark energy, meaning dark energy whose density or behavior changes over time, rather than remaining fixed. The most studied class of these models involves a hypothetical scalar field called quintessence, a field that fills space uniformly the way the Higgs field fills space, but whose energy density evolves over time as the field rolls through some potential energy landscape. In quintessence models, the effective dark energy density changes as the universe evolves. It might be stronger in the past and weaker now, or weaker in the past and growing stronger now, or oscillating between stronger and weaker phases in a pattern tied to the details of the field's potential. The equation of state parameter, conventionally denoted W, is the key mathematical quantity that distinguishes different dark energy models. It measures the ratio of the dark energy's pressure to its energy density. For a true cosmological constant, W equals exactly -1. For quintessence models with a slow-rolling scalar field, W is greater than -1. For a particularly exotic class of models called phantom energy, W is less than -1. These might sound like abstract distinctions, but they have dramatically different implications for the long-term fate of the universe, as you are about to see. The thing that makes all of this genuinely uncomfortable from a theoretical perspective is that we do not have a compelling, accepted explanation for why dark energy has the value it does, whether that value is constant or evolving, whether it is a property of the vacuum or a dynamic field, whether it is fundamental or emergent. We have a mathematical description of what dark energy does. We do not have a physical understanding of what dark energy is. When physicists speak of the cosmological constant problem, they are talking about this gap between description and understanding. We can insert the cosmological constant into Einstein's equations and it works beautifully. The predictions match the observations. But the value of that constant is inexplicable. It is a free parameter, a number that must be put into the theory by hand, extracted from observation, with no deeper theory that predicts or derives it. For a quantity that controls the ultimate fate of the entire universe, that level of ignorance is, at minimum, unsatisfying. At maximum, it is a signal that our theoretical framework is missing something fundamental. The most active experimental effort to characterize dark energy is happening right now, and the most surprising results have come in the last 2 years. What those results suggest is that dark energy may not be the simple cosmological constant cosmologists had settled on as their working assumption. The evidence is not yet definitive, but it is compelling enough to have fundamentally changed the mood of the field. Part 5. The Deci Bombshell and a Universe Changing Its Mind. In April 2024, the Dark Energy Spectroscopic Instrument released its first major data results, and the field of cosmology has been talking about almost nothing else ever since. Deci is unlike any previous dark energy instrument in its scope and ambition. Installed on the Mayall 4-meter telescope at Kitt Peak in Arizona, it uses 5,000 robotic optical fibers that can each be repositioned in seconds to point at different galaxies simultaneously. On any given night, Deci can measure the spectra of tens of thousands of galaxies, extracting from each one its distance and recession speed with high precision. The goal is to map the three-dimensional distribution of millions of galaxies across vast volumes of cosmic history, and use that map to trace how the expansion rate has changed over cosmic time. The technique Deci uses as its primary tool is called baryon acoustic oscillations. In the extremely hot, dense early universe, before atoms could form, matter and radiation were coupled into a single plasma, and pressure waves, sound waves effectively, moving at roughly 57% of the speed of light, propagated through this plasma in all directions. When the universe cooled enough for electrons and protons to combine into neutral atoms and radiation to decouple from matter, those pressure waves froze in place, leaving a faint but precise imprint in the distribution of matter, a slight excess of galaxies separated from each other by a characteristic distance corresponding to how far those sound waves had traveled before freezing. This preferred separation, about 500 million light-years in today's universe, is called the baryon acoustic oscillation scale, and it serves as a cosmic ruler. By measuring this scale at different distances, and therefore at different epochs in the universe's history, Deci can trace the expansion history with precision. Deci's first-year data, covering more than 6 million galaxies, across a substantial range of cosmic time, revealed something that made cosmologists simultaneously excited and uneasy. The data, when combined with information from the cosmic microwave background and supernova surveys, showed a preference for dark energy that is not constant. The equation of state appears to have evolved over cosmic time in a way that the simple cosmological constant does not predict. Specifically, the data suggested that dark energy was stronger in the past and may be weakening today, or more technically, that the equation of state parameter has been moving from values more negative than -1 toward values closer to -1 or even above -1 in recent cosmic history. DESI's second year of data, released in April 2025, covered more than double the number of cosmic objects and strengthened the case for dynamic dark energy. Adam Rees, one of the original discoverers of dark energy, called the possibility that it is evolving the best news he had heard since the original discovery, more than 25 years earlier. Michael Turner, the cosmologist who coined the term dark energy, called it deeply intriguing. Even cautious scientists acknowledged that if the DESI results held up with continued data collection, they would represent a genuinely major shift in our understanding of cosmic expansion. Around the same time, a separate analysis by a team at the Royal Astronomical Society using corrected supernova data, combined with the DESI baryon acoustic oscillation measurements, found something even more striking. The corrected analysis indicated that the universe's expansion may have already transitioned from accelerating to decelerating, not in the far future, as the result of dark energy gradually weakening, but now. The transition, in their analysis, would have occurred in the relatively recent cosmic past. The universe, according to this picture, is already slowing down, and if the trend continues, the expansion rate will continue to decline. These results are not universally accepted. The data analysis methods are being scrutinized carefully. The statistical significance, while notable, has not yet reached the 5 sigma threshold that would conventionally announce a confirmed discovery in physics. Alternative explanations, including the possibility that systematic errors in the supernova data are mimicking the appearance of evolving dark energy, are actively being investigated. But the direction of the evidence is striking, and it points towards something that was, until very recently, considered a minority position in cosmology. Dark energy may not be a simple constant. It may be a dynamical quantity, evolving over cosmic time in ways that are only now beginning to be measurable. And if that is true, the ultimate fate of the universe is genuinely uncertain in a way that goes beyond the technical uncertainties of measuring the cosmological constant precisely. The future of cosmic expansion depends on the behavior of something that is changing, and we do not yet know where it is going. Cornell University physicist Henry Tai published a paper in 2025 arguing that the DESI and dark energy survey data actually indicate a negative cosmological constant, which would imply that the universe will eventually collapse in a big crunch, something considered almost impossible just a few years ago given the apparent acceleration. His claim is controversial and has not achieved consensus, but the fact that it is being seriously published and debated in the scientific literature tells you how much the evidential landscape has shifted. The honest summary of where things stand as of mid-2026 is this. Dark energy is the dominant component of the universe, controlling its expansion. Whether that dark energy is constant or evolving remains genuinely unclear, with recent evidence tilting toward evolution. If it is evolving and weakening, the fate of the universe could range from the quiet heat death of a forever expanding cosmos, slowly cooling to nothing, to a reversal of expansion and eventual gravitational collapse, to some intermediate scenario we have not yet characterized. The situation is not resolved, the data are in, but the picture they are painting is still developing. To understand what each possible outcome would actually look like, we need to walk through the major scenarios individually, not as abstract theoretical constructs, but as physical realities with specific timelines and specific consequences, playing out across timescales that are genuinely difficult to hold in your mind, but that can be described with precision by the mathematics of cosmology. Part 6. Scenario 1. The Big Freeze. The Big Freeze, sometimes called the heat death or the Big Chill, is currently the most widely accepted long-term fate of the universe, under the assumption that dark energy behaves as a cosmological constant or weakens slowly over time. It is not a dramatic ending. It is the quietest possible conclusion to the story of the cosmos, a universe that expands forever, gradually cooling, slowly dimming, asymptotically approaching a state of maximum entropy, where nothing changes, nothing happens, and time continues only as an abstract parameter, with no physical process to mark its passage. To walk through this scenario properly, you need to start where we are now and follow the thread of time forward over scales that are genuinely alien to human intuition. Right now, we live in what cosmologists call the stelliferous era, the age of stars. This era began several 100 million years after the Big Bang, when the first stars ignited, and it will end roughly 100 trillion years from now, when the last stars go dark. 100 trillion years sounds like a very long time. It is. The current age of the universe is approximately 13.8 billion years. 100 trillion years is more than 7,000 times that. But in the context of the timeline of the Big Freeze, it is just the first act. Stars exist by fusing hydrogen into helium in their cores, releasing energy as light and heat that supports the star against its own gravity. The more massive a star, the faster it burns, and the shorter its life. Massive stars, tens of times the sun's mass, live only a few million years before exploding as supernovae. Sun-like stars live about 10 billion years. But the majority of stars in the universe by number are dim, cool red dwarfs, objects about a tenth the mass of the sun that burn their hydrogen so slowly and so efficiently that they can shine for trillions of years. The last red dwarf stars, the universe's most patient and persistent lights, are expected to finally exhaust their fuel and fade to cold, inert cinders, roughly 100 trillion years from now. When those last red dwarfs finally go dark, what remains is a universe populated by the cooling corpses of dead stars. White dwarfs, the dense remnants left when stars like the sun shed their outer layers in their final stages, slowly radiate their residual thermal energy into space. Neutron stars, the extraordinarily dense remnants of stellar explosions, cool over comparable timescales. Black holes, formed from the most massive stellar deaths, do not cool in the conventional sense, but persist as gravitational wells that slowly accumulate mass from whatever sparse matter crosses their event horizons. This is the degenerate era, and it stretches from roughly 100 trillion years to approximately 10 to the 40th power years into the future. During this period, the universe is not entirely dead, but it is quieter than any environment you can imagine. White dwarfs cool and eventually become hypothetical objects called black dwarfs, stellar remnants so cold they no longer emit any detectable radiation. No confirmed black dwarf yet exists in the universe, because the oldest white dwarfs are still hot enough to glow faintly, and the timescale for cooling to true blackness exceeds the current age of the cosmos. There is a speculative process that would accelerate the timeline during this era. Most grand unified theories in physics predict that protons, the positively charged particles at the heart of every atomic nucleus, are not absolutely stable. Given enough time, a proton will decay into lighter particles through a process that violates baryon number conservation. Current experiments have constrained the proton's half-life to be at least 10 to the 34th power years. If proton decay occurs, and we do not know for certain that it does because no one has ever observed it, then the timescale from 10 to the 34th power to 10 to the 40th power years would see all ordinary matter, every atom in every white dwarf and neutron star and cold dead planet, slowly disintegrate into a haze of electrons, positrons, and photons. Every solid object that has survived to that point, everything made of ordinary baryonic matter, would dissolve not through any dramatic event, but through the quiet statistical certainty of particle instability. Whether proton decay occurs or not, by roughly 10 to the 40th power years into the future, the universe enters the black hole era. This is the period when black holes are the most significant structures remaining in the cosmos. The stellar mass black holes formed by the deaths of massive stars will still be there. The supermassive black holes, millions or billions of solar masses, that currently lurk at the centers of galaxies will have grown somewhat through continued accretion of the sparse remaining matter, and through the mergers that occurred when galaxies themselves eventually collided and merged. In an accelerating universe, galactic clusters ultimately remain bound together by gravity, even as the space between clusters expands. The galaxies within each cluster will eventually merge, their central black holes combining into ever more massive objects. But even black holes do not last forever. Stephen Hawking showed in 1974, through a calculation combining quantum mechanics with the geometry of black hole event horizons, that black holes are not perfectly black. They emit a slow trickle of thermal radiation, now called Hawking radiation, produced by quantum processes near the event horizon. This emission is extraordinarily faint for stellar mass black holes and is utterly negligible compared to the rate at which those black holes are absorbing radiation from the cosmic microwave background, which is currently warmer than any Hawking emission would be. But as the universe expands and cools, and the background radiation temperature drops toward absolute zero, the Hawking emission from black holes eventually exceeds what they receive from the environment, and they begin to lose mass. The evaporation rate is extremely slow for massive black holes. A stellar mass black hole, perhaps 10 times the mass of the Sun, would take approximately 10 to the 67th power years to completely evaporate through Hawking radiation. A supermassive black hole of 1 billion solar masses would take about 10 to the 96th power years. The most massive black holes in the universe, those that grew to perhaps 10 to the 11th power solar masses through mergers and accretion over the previous cosmic ages, would persist for roughly 10 to the 100th power years, one followed by 100 zeros, a Google years. When the last black hole finally evaporates, what remains is the dark era. The universe contains no complex structures, no atoms if proton decay has occurred, no black holes, no white dwarfs. Just an expanding, cooling void, carrying a very dilute bath of photons, neutrinos, electrons, positrons, and perhaps some exotic relics from the early universe, all moving through space that is growing emptier and colder with every passing moment. The temperature of this radiation approaches absolute zero asymptotically, but never reaches it. The entropy of the universe has reached or closely approached its maximum. There are no temperature differences large enough to drive any thermodynamic process. There is no usable energy anywhere in the cosmos. This is the heat death. Not an explosion, not a collapse, not any single dramatic event, just the quiet, patient end of all difference, all structure, all complexity. As the universe achieves the equilibrium it has been approaching since the moment of its birth. In this state, the universe still exists in a technical sense. Space still exists, still expands, still has geometric properties. But nothing happens. Nothing can happen. Time continues to flow, but there is nothing left to mark its passage. The Big Freeze is the most probable ending if dark energy is truly a cosmological constant, or something very close to it, and if protons eventually decay. It is not a particularly romantic end, but there is something honest about it. A universe that has burned brilliantly for a finite time, and then settled into perfect stillness. All the energy that was, spent. All the structures that could form, formed and dissolved. All the stories the cosmos could tell, told. Whether it is the actual ending remains to be determined, because the other scenarios are very different, and some of them are not quiet at all. Part 7, Scenario 2, The Big Rip. Imagine standing outside on a quiet night and watching the stars overhead. Now imagine that the stars begin to move, not in the way stars appear to drift over the course of hours as the Earth rotates, but visibly, noticeably, separating from each other in real time, the constellations you know dissolving as their component stars pull apart. Then the more distant galaxies, those faint smears visible to the naked eye or through a telescope, begin to tear into component parts. Then the sun loosens its gravitational hold on the planets, and they drift away into an expanding void. Then the Earth itself, no longer held together by its own gravitational compression against the repulsive force now operating on all scales, comes apart. Then the molecules in your body no longer hold together. Then the atoms themselves disintegrate, their electrons no longer bound to their nuclei. Then the atomic nuclei, protons and neutrons held together by the strong nuclear force, are ripped apart. And then, a fraction of a second after the atomic nuclei dissociate, the scale factor of the universe reaches infinity, and the cosmos, as we understand it, ceases to exist. This is the Big Rip, and it requires taking seriously the possibility that dark energy does not behave like a cosmological constant. The key quantity is once again the equation of state parameter W. For a cosmological constant, W equals exactly -1. In this case, the energy density of dark energy remains constant even as the universe expands, and while the expansion accelerates, the acceleration itself remains finite and bounded. Galaxies and galaxy clusters remain gravitationally bound. Stars and planets and atoms remain intact. The Big Rip does not occur. But if dark energy is a form of phantom energy, meaning its equation of state parameter W is less than -1, something different happens. In phantom energy models, the dark energy density does not merely stay constant as the universe expands. It actually increases. As space grows, the repulsive energy of space grows with it. The expansion rate does not just remain accelerating, it accelerates at an ever-increasing rate, growing without bound, diverging to infinity in a finite amount of time. The Big Rip scenario was formalized in 2003 by Robert Caldwell of Dartmouth College and his colleagues. In a representative calculation, using an equation of state parameter of -1.5, the Big Rip would occur approximately 22 billion years in the future. That is less than twice the current age of the universe. Not an eternity, a specific, calculable time at which everything ends. The timeline to that ending is detailed and precise enough to trace step by step. About 1 billion years before the final moment, dark energy begins to overwhelm the gravitational bonds holding galaxy clusters together. The vast networks of gravitationally associated galaxies that today form the nodes of the cosmic web begin to dissolve. Individual galaxies drift apart from their clusters. About 60 million years before the end, the galaxy clusters are already fully dispersed, and now the dark energy is strong enough to overwhelm the gravitational bonds within individual galaxies. The stars of the Milky Way, held in orbit around the galactic center by collective gravity, begin to scatter. The Milky Way itself comes apart. Its spiral arms unwind and dissolve into a dispersing cloud of individual stars, each moving independently through a rapidly expanding void. 3 months before the final moment, the force of dark energy, on scales comparable to our solar system, becomes strong enough to overcome the sun's gravitational hold on the Earth and the other planets. The planets drift away from the sun, not hurled outward violently but simply untethered, their orbital bonds dissolved by the ever-growing repulsive force of phantom energy operating on the space between them and their star. The solar system ends. 30 minutes before the end, the Earth itself cannot hold together. The gravitational compression that makes a planet a coherent spherical body is overpowered, and the planet comes apart. Not in an explosion, but in a dissolution, the rock and iron and water dispersing as the space within the planet itself grows faster than gravity can counteract. 1/10,000th of a femtosecond before the final moment, roughly 10 to the -19th power seconds before the Big Rip, atomic nuclei can no longer hold together. The strong nuclear force, the most powerful of the 4 fundamental forces of nature, the force that binds protons and neutrons together against the electromagnetic repulsion of their positive charges, is overwhelmed by dark energy operating on the scale of atomic nuclei. Every nucleus in the universe disintegrates simultaneously. Atoms cease to exist. And then the scale factor of the universe reaches infinity. The Big Rip. How likely is this? Current observational data, including the results from Planck, from the various supernova surveys, and from DESI's baryon acoustic oscillation measurements, are consistent with an equation of state parameter very close to -1. The Planck collaboration found a value of approximately -1.028 plus or minus 0.031, meaning that values slightly less than -1, which would imply phantom energy and a future Big Rip, are within the measurement uncertainty. The Big Rip is not the most probable scenario given current data, but it is not ruled out. The DESI results add a further complication. If dark energy is evolving and its equation of state parameter is changing over time, the question of whether phantom energy behavior is present becomes more nuanced. Dark energy could cross what cosmologists call the phantom divide, transitioning from behavior with W below -1 to behavior with W below -1, or vice versa, over cosmic history. Some parameterizations of the DESI data hint at exactly this kind of crossing. If the dark energy equation of state has recently dropped below -1 and continues in that direction, the Big Rip becomes not just a theoretical possibility, but a genuine forward projection of currently observed behavior. The Big Rip is the most violent of the universe's possible endings. But violence here is relative. The process would unfold over tens of billions of years from a human perspective, and the final escalation would be invisible to anyone not specifically looking for it until the last few million years before the galaxies begin to dissolve. Life, if it existed, would notice the sky changing. The familiar galactic companions would drift away. The night sky would empty. And then, in the final hours and minutes, everything would come apart so rapidly that there would be no time to process it. Part 8, Scenario 3, The Big Crunch. For most of the 20th century, before the discovery of dark energy's existence, let alone its apparent acceleration, the Big Crunch was considered the primary alternative to eternal expansion. It was the scenario in which gravity eventually wins. The expansion of the universe slows, stalls, and reverses. Galaxies that are currently moving apart begin to approach each other. The cosmic microwave background radiation, which is today a dilute whisper of photons, at a temperature of just 2.725 degrees above absolute zero, begins to warm as the contraction compresses it. Galaxies merge and collide. Stars stream out of their disks and crash into each other. The gas between galaxies heats up. The night sky, which is dark because the universe is large and cold and old, becomes blazing hot as everything compresses toward a single point. The Big Crunch is the time reversal of the Big Bang, a singularity, a point of infinite density and temperature, beyond which general relativity's equations break down, and no prediction is possible. The discovery of accelerating expansion in 1998 seemed to close the door on this scenario. If dark energy is pushing space apart and doing so with ever-increasing force, then gravity cannot reassert itself on the largest scales. The expansion would continue forever. A Big Crunch seemed to require not just the absence of dark energy, but active contraction, and the data seemed to rule that out decisively. But the DESI results have reopened the conversation. If dark energy is dynamical, if its equation of state parameter is evolving over time, the future behavior of dark energy is no longer determined by a single fixed number. An evolving dark energy could weaken over cosmic time. It could decline from its current value toward zero and then continue into negative territory. If the effective dark energy density becomes negative, it no longer acts as a repulsive force, but as an additional attractive force, working alongside ordinary gravity to slow and eventually reverse the expansion. The universe could stop expanding, hold for a period at maximum size, and then begin to contract. Cornell physicist Henry Tye's 2025 analysis of the DESI and dark energy survey data drew attention because it argued that the observed patterns are most consistent with a cosmological constant that is effectively negative, implying that a Big Crunch is not just possible, but perhaps the most likely eventual fate. His claim is contested and has not achieved widespread acceptance, partly because the interpretation of the DESI results is still evolving, and partly because negative cosmological constants create additional theoretical complications. But it has been published, discussed, and taken seriously by a subset of the community. What would a Big Crunch actually look like as an experience, if you could be present through the full arc of a collapsing universe? The early stages of the collapse would be imperceptible. The expansion would slow gradually over billions of years. The recession of distant galaxies would decelerate. Eventually, the most distant galaxies would stop moving away and begin, almost imperceptibly at first, to approach. The redshift of their light would gradually decrease, then reach zero, and then the light would begin to blue shift, its wavelength compressed as the galaxies moved toward us rather than away. As the collapse accelerated, the density of the universe would increase. The temperature of the background radiation would rise. Stars and galaxies would begin to collide and merge with increasing frequency. The night sky would grow brighter as the universe compressed and the background radiation warmed. At some point, the temperature of the background radiation would exceed the surface temperature of stars, and stars would no longer be able to radiate energy into space because the surrounding environment would be hotter than they were. They would be cooked from outside rather than heated from within. The final stages of collapse would occur on increasingly short timescales. Everything would compress together. The distinction between stars and galaxies and the space between them would dissolve. And then the singularity, the point at which general relativity's equations produce infinities and physics as currently understood, breaks down entirely. Whether there is something beyond the singularity is unknown. The Big Bounce hypothesis proposes that the collapse would trigger a new expansion, essentially a new Big Bang, with the universe cycling through endless expansion and contraction phases. This is not predicted by general relativity, which simply breaks down at the singularity, but there are theoretical frameworks in quantum gravity that suggest the singularity is not truly infinite, and that some kind of bounce is possible. The cyclic cosmology models of Paul Steinhardt and Neil Turok, for example, describe a universe that bounces repeatedly between expansion and contraction phases, each cycle potentially generating a universe with slightly different properties. Whether any of these scenarios could preserve information from the previous cycle, whether our Big Bang was itself the bounce from a previous collapse, whether there is any physical continuity or just a reset to arbitrary initial conditions, these remain genuinely open questions. The singularity sits at the edge of current theoretical understanding, and what lies beyond it, if anything meaningful can be said to lie beyond it, requires a theory of quantum gravity that we do not yet possess. What the current DESI data suggest, if they hold up, is that the Big Crunch should no longer be treated as a definitively ruled-out option. The fate of the universe remains genuinely uncertain. The data are still coming in. Part 9. The cosmological constant and the vacuum we do not understand. There is a question underneath all the scenario building, underneath the debate about the Hubble constant and the interpretation of DESI's baryon acoustic oscillation measurements. That gets to the heart of why dark energy is such a profound problem for physics. It is not just a question about what will happen to the universe in the distant future. It is a question about why the universe has the properties it has right now, and whether those properties could have been different. Consider the cosmological constant in the way a theoretical physicist considers it. If dark energy is a cosmological constant, it represents the energy density of the vacuum, the lowest possible energy state of quantum fields. Quantum field theory, the theoretical framework that underlies our most precise predictions in particle physics, tells us that the vacuum is not empty. Every quantum field, whether it is the electromagnetic field, the electron field, the quark fields, the Higgs field, or any other, has a ground state energy that is not zero. In quantum mechanics, you cannot have a system with exactly zero energy in its ground state. There is always a zero-point energy, an irreducible minimum that persists even when the system is in its lowest possible state. Sum up the zero-point energies of all the quantum fields in the standard model of particle physics, and you get a vacuum energy density. The magnitude of this sum depends on where you cut off the calculation. Quantum field theory is a framework built on continuous fields, and naive calculations produce divergent results unless you impose a maximum energy scale, called a cutoff, above which the theory is assumed to break down. If you cut off at the Planck energy, the energy scale at which quantum gravitational effects are expected to become important, the calculated vacuum energy density is approximately 10 to the 120th power times larger than the observed dark energy density. If you cut off at the electroweak energy scale, the energy of the Higgs mechanism, the mismatch is approximately 10 to the 55th power. These are not small discrepancies that might be resolved by better calculations. They are catastrophic mismatches between theoretical expectation and observational reality, suggesting that some physical mechanism is suppressing the vacuum energy by an extraordinary and precise amount, leaving behind only the tiny residual we observe. No known mechanism achieves this. Supersymmetry, the theoretical framework that proposes a symmetry between particles and their force-carrying counterparts, would naturally cancel many contributions to the vacuum energy if it were an exact symmetry of nature. But supersymmetry, if it exists, must be broken in a way that leaves a residual energy comparable to what the symmetry breaking produces, which is still far too large. The anthropic argument, frequently invoked in discussions of the cosmological constant, suggests that the value we observe is constrained by the requirement that observers exist to observe it. If the cosmological constant were much larger than observed, the universe would have expanded too rapidly for galaxies and stars to form, and no observers would be present to measure it. If it were much more negative, the universe would have collapsed before stars and planets formed. There is a range of values compatible with the existence of complexity and life, and the observed value falls within that range. In the context of a multiverse where different regions of space have different effective values of the cosmological constant, the anthropic selection of values compatible with observers might explain why we find ourselves in a universe with the cosmological constant we measure, without requiring a dynamical mechanism to produce it. This argument is controversial and deeply unsatisfying to many physicists because it does not predict anything. It is not a mechanism. It is a selection principle that tells you why you observe a particular value without telling you where that value comes from physically. It explains the fine-tuning problem by multiplying it into an even more extravagant scenario, the vast multiverse, in which all possible values occur somewhere, and life simply finds itself where the conditions allow it to exist. Whether the cosmological constant is a fundamental property of space, a dynamical field, the result of anthropic selection in a multiverse, or the consequence of physics we have not yet discovered, is one of the most important open questions in all of science. It underlies not just cosmology, but fundamental physics. The answer would tell us something profound about the relationship between the quantum world and the large-scale geometry of spacetime, about whether the universe's properties are the result of deep physical law or contingent initial conditions, about whether there is a single universe or an uncountable infinity. None of these questions are currently answered, but they are being pursued with extraordinary tools, and those tools are generating data that is actively reshaping the debate. Part 10. What astronomers are actually doing right now. While theorists debate the nature of dark energy and the ultimate fate of the universe, observational cosmologists are building and deploying instruments of unprecedented power to constrain the answer. The current decade is arguably the most productive in the history of observational cosmology, with multiple major facilities coming online simultaneously and generating data at rates and precision levels that were unimaginable a generation ago. DESI, as we have discussed, is the most immediate presence in this story. Its 5-year survey, which began in earnest in 2021, is expected to catalog more than 35 million galaxies and quasars, producing the largest three-dimensional map of the universe ever constructed. The baryon acoustic oscillation measurements from that map will constrain the expansion history of the universe across a range of cosmic times with a precision that will either confirm or strongly challenge the cosmological constant picture. The first 2 years of data have already moved the field significantly. The full 5-year dataset, expected to be completed and analyzed in the late 2020s, will either resolve the tension between the cosmological constant and dynamic dark energy models, or deepen the mystery if the hints of evolution in the current data strengthen into a definitive detection. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is conducting a wide-area survey of billions of galaxies from the visible and near-infrared sky, measuring both their shapes and their distances across a large fraction of the sky. The shape measurements allow Euclid to probe weak gravitational lensing, the subtle distortion of galaxy shapes by the gravitational influence of all the matter between the galaxy and the observer. These distortions are sensitive to the growth of structure in the universe, which depends on both the expansion history driven by dark energy and the clustering properties of dark matter. Together, Euclid's lensing and spectroscopic measurements will provide complementary constraints on dark energy to those from DESI. Early Euclid data releases in 2024 and 2025 have already revealed remarkable images of the distant universe and begun to deliver science results. The full survey, expected to cover 15,000 square degrees of sky and several billion galaxies over its 6-year primary mission, will be transformative. NASA's Nancy Grace Roman Space Telescope, named for the astronomer often called the Mother of Hubble for her crucial role in planning the Hubble Space Telescope, is expected to launch in 2027 and conduct a wide-field survey complementary to Euclid and DESI. Roman has a field of view 100 times larger than the Hubble Space Telescope's primary instrument, while maintaining comparable resolution, making it extraordinarily efficient for wide-area surveys. Its dark energy program will use Type 1 supernovae, weak lensing, galaxy clusters, and baryon acoustic oscillations simultaneously, cross-checking constraints from multiple independent methods against each other. If there is a systematic error in any one method, cross-comparison with others should reveal it. The James Webb Space Telescope, launched in December 2021, has already transformed the study of the early universe and galaxy formation. Its extraordinary sensitivity in the near and mid-infrared allows it to observe galaxies at redshifts previously inaccessible, probing the universe as it was just hundreds of millions of years after the Big Bang. Webb's observations have revealed galaxies that formed earlier and were more massive than many models predicted, creating productive tension with simulations of early galaxy formation, and suggesting that our understanding of the first billion years of cosmic history is still incomplete. For the expansion history problem specifically, Webb is contributing through its precise measurements of Cepheid variable stars at distances the Hubble Space Telescope could not cleanly resolve, providing the highest quality local distance measurements yet obtained, and contributing to the Hubble constant debate from the observational side. The Vera C. Rubin Observatory, currently being commissioned at Cerro Pachón in Chile, will conduct the Legacy Survey of Space and Time, starting in the mid-2020s, imaging the southern sky repeatedly over a 10-year period and building a time-domain picture of the universe unprecedented in scope. Among its dark energy science targets are the detection and characterization of tens of thousands of Type 1a supernovae, extending the supernova distance ladder to larger distances and larger samples than previously possible. Its statistical power will be formidable, and its combination with DESI, Euclid, and Roman will allow multi-probe dark energy analyses of extraordinary power. Underlying all of this observational activity is a growing computational infrastructure. The simulations required to model the universe from the initial conditions set by inflation, through the growth of large-scale structure, through the formation and evolution of galaxies, and into the future, are extraordinarily demanding. Modern cosmological simulations run on supercomputers with thousands of processors for months, modeling billions of particles representing dark matter, gas, and stars across cosmological volumes. The illustrious TNG simulations, the Eagle simulations, the Bahamas simulations, these computational models of the universe provide theoretical predictions against which observations can be compared and tested, allowing researchers to ask what the universe should look like if dark energy has this property or that property, and then compare to what is actually seen. The synergy between observation and simulation has never been tighter. As observational datasets grow to encompass hundreds of millions or billions of galaxies, the statistical precision of the constraints they provide can only be fully exploited if the theoretical predictions against which they are compared are equally precise. Both sides of this program are advancing rapidly, and the convergence will determine whether the cosmological constant is real and fixed or dynamic and evolving. There are also experiments underway that approach the dark energy question from a completely different angle: the direct detection of gravitational waves from cosmological sources. The LISA mission, the Laser Interferometer Space Antenna being developed by the European Space Agency with NASA partnership for a launch in the late 2030s, will detect gravitational waves from merging supermassive black holes at cosmological distances. These mergers provide a completely independent standard siren, using gravitational wave amplitude rather than electromagnetic luminosity to determine distances, and by combining with redshift measurements of the host galaxies, they will provide a new and completely independent measurement of the Hubble constant. If the gravitational wave Hubble constant agrees with the early universe Planck value, it points toward a systematic error in the distance ladder. If it agrees with the late universe supernova value, it strengthens the case for new physics. Every one of these instruments, every one of these approaches, is asking a version of the same question. What is dark energy, and what will it do? The answer to that question determines which of the scenarios we have described will actually unfold, over timescales that dwarf the current age of the universe by factors that make the numbers themselves feel almost fictional. Part 11. The Final Reckoning. What do we actually know? After following this thread from Edwin Hubble's mountaintop observations in 1929 to the DESI results of 2025, from the quiet mechanism of baryon acoustic oscillations to the violence of the Big Rip, from the cosmological constant problem to the observational infrastructure of a generation of astronomers and physicists pointing their finest instruments at the largest question, it is time to take honest stock of where things stand. Not a tidy conclusion, not a satisfying resolution, but an honest accounting of what we know, what we think we know, what we suspect, and what remains genuinely, openly, irreducibly uncertain. We know, with extraordinary confidence, that the universe is expanding. This is among the most thoroughly tested facts in all of science. The redshifts of galaxies, the large-scale structure of the cosmic web, the existence and properties of the cosmic microwave background, the primordial abundances of light elements produced in the first 3 minutes after the Big Bang, the evolution of galaxy populations over cosmic time, all of these independent lines of evidence converge on a universe that has been expanding for approximately 13.8 billion years from an initial hot, dense state. The expansion is not in doubt. We know, with nearly equal confidence, that the expansion is currently accelerating. The supernova data that revealed this in 1998 have been confirmed many times over using independent methods. The acceleration has been measured in the pattern of galaxy clustering, in the cosmic microwave background, in the integrated Sachs-Wolf effect, visible in the correlation between the CMB and large-scale structure, and in the baryon acoustic oscillation scale at different cosmic epochs. The acceleration is real. We know that the acceleration is driven by some form of dark energy that makes up approximately 68% of the total energy content of the universe. The existence of this dark energy component is required by the geometry of the universe, which is flat to within measurement precision, and by the detailed pattern of expansion history inferred from multiple observational probes. Without something like dark energy, the pieces do not fit. What we do not know is whether dark energy is truly constant or dynamically evolving over time. The evidence from DESI and the Dark Energy Survey collected through 2024 and 2025 hints at a statistically significant but not definitively conclusive level at an equation of state that is changing, suggesting that dark energy may have been stronger in the past and is weakening today, or that it has recently crossed from one behavior regime to another. This is the central open question in observational cosmology, and it is being pursued with every major current and planned survey instrument. We do not know the physical nature of dark energy, whether it is the vacuum energy of quantum fields, a rolling scalar field, a modification of general relativity on cosmological scales, or something altogether beyond the current theoretical catalog. No physical model of dark energy has achieved consensus or made new predictions confirmed by experiment. The cosmological constant works as a description. It does not work as an explanation. We do not know the ultimate fate of the universe. This is not a failure. It is the present state of genuine scientific inquiry. The fate depends on dark energy's behavior over cosmic time, which we are actively measuring. If dark energy is constant, the Big Freeze is the most likely ending, playing out over timescales measured in units like 10 to the 100th power years. If dark energy is phantom energy, with W significantly below -1, the Big Rip becomes possible, or even likely, on timescales as short as tens of billions of years. If dark energy is weakening, and eventually reverses sign, the Big Crunch is not ruled out, and theoretical work published in 2025 suggests the DESI data are consistent with this scenario. There is something deeply beautiful about this state of affairs if you approach it with the right perspective. The question of what the universe will ultimately do is not merely philosophical. It is not beyond the reach of measurement. It depends on specific physical quantities, the equation of state parameter of dark energy at various redshifts, that real instruments deployed at real observatories are measuring right now. The fate of the universe is a scientific question, and we are in the process of answering it through empirical observation. Every night that DESI is operational, its 5,000 robotic fiber positioners click into position, pointing at galaxies scattered across billions of light-years of cosmic distance, measuring the spectrum of each one, and recording the precise wavelength of the baryon acoustic oscillation imprint. Every image Euclid captures of the weak lensing signature in the shapes of hundreds of millions of galaxies is a constraint on the equation of state. Every Type 1a supernova the Rubin Observatory will detect and characterize is another data point on the distance redshift relationship that was the original diagnostic of dark energy. The answer is being built, one measurement at a time, out of the accumulated precision of thousands of observations. What happens when we finally have enough data to answer definitively? When the equation of state parameter is measured to the precision needed to distinguish constant from evolving, to rule in or rule out each of the scenarios we have described. If dark energy is a true cosmological constant, we will have confirmed that the universe is heading for the big freeze, and the intellectual focus will shift from what will happen to why does the universe have this exact constant? The cosmological constant problem will remain unsolved, but the empirical question of the cosmic fate will be closed. If dark energy is dynamical and weakening, the question becomes whether that weakening leads to a gentle asymptotic approach to zero, a reversal into negative territory producing eventual collapse, or some oscillatory behavior that neither freezes nor collapses, but cycles through expansion and contraction phases. Each of these would be a discovery of the first order, reshaping our understanding of fundamental physics and cosmology simultaneously. If dark energy turns out to be phantom energy, growing stronger over time rather than weakening, the Big Rip becomes the predicted fate, and the measured timeline for that ripping would give the universe's remaining lifespan, potentially measurable in billions, rather than the incomprehensible numbers associated with the Big Freeze. Any of these answers would be extraordinary. Any of them would tell us something fundamental about the nature of space and energy, and none of them will be known for certain without the data we are still in the process of collecting. There is a version of this story that emphasizes how little we know, that treats the uncertainty as a frustrating incompleteness, a failure to reach the answer. But there is a better version, one that is truer to the actual experience of science. We live in the moment when the question became answerable. We live in the era when the instruments are precise enough to constrain the equation of state of dark energy, when the sky surveys are comprehensive enough to map the baryon acoustic oscillation scale across half the age of the universe, when the theoretical understanding is deep enough to translate those measurements into predictions about trillions and quadrillions of years hence. We are not waiting for the answer. We are the generation that is finding it. The universe has been expanding for nearly 14 billion years. Whether it will expand for another 20 billion before tearing itself apart, or for another 100 trillion before the last stars go dark, or for another Google before the last black hole evaporates, or whether it will one day reverse and fall back into itself. None of these possibilities have been ruled out. All of them are being tested. The answer is out there, encoded in the subtle clustering of galaxies, in the precise shape of the baryon acoustic oscillation peak, in the apparent brightness of supernovae so distant their light has traveled for billions of years to reach us. Every photon that enters a spectrograph, every galaxy whose distance and recession speed gets added to the survey catalog, every new measurement of the Hubble constant from an independent method, every supernova catch by a wide-field camera, all of it is accumulating toward the answer. All of it is narrowing the uncertainty around the most consequential number in cosmology, the equation of state parameter of dark energy at the current epoch of the universe. We are, collectively, looking up at a sky full of dying light from the deep past, using that ancient radiation to predict the deep future. We are writing the last chapter of the universe before we know how it ends. And that combination of ignorance and precision, of profound uncertainty, constrained by exquisite measurement, is what makes this the most remarkable time in the history of cosmology to be paying attention. The universe may stop expanding. It may never stop. It may stop and reverse. It may expand so violently that it tears itself apart. It may cool to infinite emptiness or collapse to infinite heat. We do not know yet, but we are finding out. And that, in the end, is not a disappointment. It is the whole point. If you made it all the way here, thank you. That is genuinely not a small thing. These questions are not easy ones, and the fact that you sat with them for this long says something about you. If you found something in this video worth keeping, a share, a like, or a subscription would mean a great deal and helps this channel reach people who spend their nights wondering about the same things you do. Leave a comment telling us which scenario you think is most likely, or which one you hope for, or which one you find most haunting. There are no wrong answers, and the conversation is one of the best parts of making these. The universe is not done with us yet, and we are not done with it. Sources and further reading. The research underlying this script draws on data from the Dark Energy Spectroscopic Instrument, DESI DR1 and DR2, the Planck Collaboration CMB results, the SH0ES team's Hubble Constant Measurements, work by Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg on the Big Rip, 2003, Fred Adams and Gregory Laughlin's Long-Term Fate of the Universe research, 1997, and peer-reviewed papers on the future evolution of the cosmos in the standard. All scenarios presented represent genuine scientific possibilities within current theoretical frameworks, labeled as speculative only where the science itself is speculative. Part 12. The Strange Geometry of an Expanding Universe. There is a misconception that almost everyone carries around when they first try to picture the expanding universe. They imagine the Big Bang as an explosion, a central point from which everything flew outward, galaxies receding away from some original ground zero like shrapnel from a bomb. In this picture, the Milky Way sits somewhere in the expanding shell of matter, moving outward from a central location, and if you could travel far enough toward the interior of the explosion, you would eventually find the place where it all began. This picture is wrong in almost every detail, and understanding how it is wrong is essential to understanding what expansion actually means, what could eventually stop it, and what is actually at stake in the question we are asking. The universe does not have a center. There is no privileged location in space from which the Big Bang originated, no point you could travel to and find the origin. The Big Bang was not an explosion of matter into pre-existing empty space. It was an expansion of space itself. Every point in the universe was the origin. The Big Bang happened everywhere simultaneously, in the same way that the surface of a balloon is everywhere simultaneously. If you draw a dot on a balloon and blow it up, the dot does not stay fixed while the rest of the surface expands away from it. The dot is on the surface, and the surface expands, and the dot expands with it. From the perspective of any dot on the balloon's surface, every other dot appears to move away from it as the balloon inflates. No dot is special. No dot is the center. The universe works this way on the largest scales, except that, instead of a two-dimensional surface embedded in three-dimensional space, it is a three-dimensional volume that may or may not be embedded in something larger, and may or may not be finite. The geometrical possibilities are more varied than the balloon analogy suggests. The universe could be positively curved, like the surface of a sphere, meaning that parallel lines eventually converge. Triangles have angles that add up to more than 180 degrees, and if you travel far enough in one direction, you eventually return to your starting point. This is a finite universe, but it has no boundary and no center. Or the universe could be negatively curved, like the surface of a saddle, where parallel lines diverge and triangles have angles summing to less than 180 degrees. This is an infinite universe. Or the universe could be flat, with the Euclidean geometry of an infinite plane extending in all directions, where parallel lines stay parallel and triangles have exactly 180 degrees. The evidence from the cosmic microwave background, particularly the pattern of temperature fluctuations on the sky as mapped by the WMAP and Planck satellites, is consistent with a flat universe to within measurement precision. The universe is flat, or so close to flat, that any curvature is undetectable at the scale of the observable universe. This flatness is itself one of the things that inflation was invoked to explain. A universe that begins with any slight curvature and then expands by the extraordinary factor inflation requires would have that curvature stretched to nearly zero on observable scales, in the same way that the surface of the Earth looks flat from ground level even though it is curved on larger scales. A flat universe, if it is truly flat and not just apparently flat on the scale we can see, is infinite. It extends without boundary or edge in every direction, filled with matter and radiation and dark energy, expanding everywhere simultaneously. The part we can see, the observable universe, is a sphere roughly 93 billion light-years in diameter, centered on us, limited not by the actual edge of the universe, but by the distance light has had time to travel to us since the Big Bang. Beyond that sphere, the universe continues in all directions, with more galaxies, more matter, the same expansion, the same large-scale structure, stretching to distances we cannot observe and may never observe. As the universe expands, this observable sphere does not grow as fast as you might expect. While the universe has been expanding for 13.8 billion years, and the speed of light is the limit for information travel, the observable universe is much larger than 13.8 billion light-years, because the universe was expanding while the light was traveling. The light we observe from the most distant galaxies was emitted when those galaxies were much closer to us than they are now. In the time that light took to travel to us, those galaxies receded, and they are now roughly 46 billion light-years away. So the observable universe has a current radius of about 46 billion light-years, not 13.8 billion. In an accelerating universe, the boundary of what is observable does not actually grow indefinitely. As expansion accelerates, galaxies that are currently just barely within our observable universe will eventually recede beyond our cosmological event horizon, the boundary beyond which no new light can ever reach us. From that moment, those galaxies are effectively gone from our universe, not in the sense that they cease to exist, but in the sense that no information about them can ever reach us. Their light, redshifted into longer and longer wavelengths, and more diluted, will never arrive. As far as our observational universe is concerned, they have vanished. This ongoing erosion of our observable universe is one of the more haunting implications of accelerating expansion. We happen to live early enough in cosmic history that we can observe thousands of billions of galaxies. But future civilizations, if any exist in the distant future when the acceleration has had billions more years to work, will look out at a sky increasingly stripped of distant light. The galaxies in the local group, bound together by gravity, will persist. Everything beyond will eventually redshift into darkness, leaving behind a cosmological horizon that contains less and less of the observable record. If you put yourself in the position of a distant civilization 100 billion years from now, living in a galaxy that has merged into the local group's final composite structure, and they build the most sophisticated telescope imaginable, they will look out at a sky far darker than ours. The Virgo cluster, some 65 million light-years away today, will be unreachable. The galaxies of the Coma cluster, at roughly 320 million light-years, will be invisible. The great cosmic web of galaxy filaments and voids that we can map today will be beyond detection. Those future astronomers, studying only the light that can reach them, will have no observational evidence that the universe contains anything beyond their local neighborhood. From their data alone, they might conclude that the universe is a relatively small collection of merged galaxies, sitting alone in an otherwise empty, infinite dark. They would have no way to know about the Big Bang, no way to detect the cosmic microwave background radiation, because it will have been redshifted to wavelengths so long and energies so low as to be effectively undetectable, and no way to construct the history of cosmic expansion that we have spent the last century uncovering. We live, in this sense, in a privileged epoch. The evidence that allows us to reconstruct the history and predict the future of the universe is still visible. The cosmic microwave background is still detectable. The distant galaxies are still observable. The baryon acoustic oscillation signal is still accessible in galaxy surveys. The data we need to understand cosmic history are available to us now, written across the sky in the red-shifted light of billions of galaxies. A civilization that arrived 1 trillion years later would find the sky nearly empty and would have no means of knowing what we know. This is not a minor observation. It means that the window of time during which a civilization can potentially understand the full history and nature of the universe is finite. We are in that window. Whether we are using it wisely is a question that each generation of scientists has to answer for itself. But the data we are collecting now, the maps of the cosmic web we are building, the measurements of the expansion history we are making, represent a kind of cosmic archaeology that becomes progressively more difficult as time goes on and the evidence fades. We are the civilization that can still read the universe's autobiography. That may not always be true. Part 13. The Geometry of Doom. How Equations Write the Future. One of the most remarkable features of modern cosmology is that the fate of the universe is not just philosophical speculation or science fiction extrapolation. It is written, in mathematical language, in a set of equations that have been tested against observations with extraordinary precision, and that, given a few key inputs, produce definitive predictions about what will happen to the universe over any time span you care to ask about. The equations in question are the Friedmann equations, derived by the Russian mathematician Alexander Friedmann in 1922 from Einstein's general relativity field equations applied to a homogeneous and isotropic universe. Friedmann died young, at 37, of typhoid fever, without knowing that his solutions would become the mathematical foundation of modern cosmology. His equations have two versions, and together they form the theoretical engine that drives every calculation about cosmic expansion. The first Friedmann equation relates the expansion rate of the universe, quantified by the Hubble parameter, to the total energy density of the universe and its spatial curvature. It says, in effect, that the rate at which the universe expands is determined by everything it contains: ordinary matter, dark matter, radiation, and dark energy. More energy density means stronger gravitational influence. The second equation determines whether the expansion is accelerating or decelerating, and it is the behavior of this equation over cosmic time that decides which of the scenarios we have described will play out. For a cosmological constant, the Friedmann equations give exponential expansion at late times. The scale factor, the number measuring how much the universe has grown since some reference epoch, grows without bound, but the Hubble parameter approaches a constant. The universe expands forever, accelerating, but the rate per unit distance is fixed. Galaxies beyond a certain distance recede faster than light and are lost to observation, but the expansion never becomes catastrophic. The Big Freeze follows from this behavior over astronomical timescales. For phantom dark energy, the Friedmann equations tell a different story. The scale factor does not just grow exponentially, it diverges to infinity in a finite amount of time. The mathematics produces what is technically called a Big Rip singularity, a point in finite future time when the scale factor is infinite, the Hubble parameter is infinite, and the expansion rate is infinite. Everything in the universe is torn apart in the approach to this singularity, as we described in Part 7. The timeline can be calculated precisely given the value of the equation of state parameter, and the more negative the value, the sooner the rip occurs. For a universe where dark energy weakens and reverses, the Friedmann equations describe a universe where the scale factor reaches a maximum and then contracts. The contraction accelerates as it proceeds, and the scale factor approaches zero in finite time. This is the Big Crunch singularity, where density and temperature diverge and general relativity breaks down. Whether there is something beyond this singularity, whether quantum gravity produces a bounce, is beyond the reach of the equations and requires physics we do not yet have. The critical insight is that each of these outcomes is a specific mathematical prediction following from specific input assumptions. The inputs are the equation of state parameter of dark energy and how it changes over time. The outputs are the precise fate of the universe. The observational programs we discussed are measuring those input parameters as precisely as possible, using the expansion history itself as the observable that constrains the parameters. Every reduction in the uncertainty on the equation of state parameter is a step toward knowing which equation, which solution, which fate, actually describes the universe we live in. Alexander Friedman wrote these equations without knowing that a century later, thousands of scientists would be deploying billions of dollars worth of technology to measure the single parameter that most constrains their solutions. He was solving a mathematical problem in general relativity, motivated by intellectual curiosity about the possible behaviors of a uniformly expanding spacetime. The universe, it turns out, was actually expanding. His equations were actually describing reality, and the key inputs those equations need to predict the future are now within observational reach, for the first time in history. Part 14. Time, Scale, and the Difficulty of Imagining the End. When cosmologists talk about the timeline to the Big Freeze, throwing around numbers like 10 to the 100th power years, or when they describe the timeline to the Big Rip in units of billions of years, these numbers pass through the mind as abstract labels without any real grip on what they mean. Part of doing this subject justice is making some effort to convey the actual scale of the times involved, even knowing that the effort will ultimately fall short. The human brain evolved to track days, seasons, and the spans of individual lives. It did not evolve to intuitively grasp what a Google years means. Start with 1 billion years. The Earth is about 4.5 billion years old, so 1 billion years is roughly a quarter of the Earth's age. The first animals with hard shells appeared about 540 million years ago. The first dinosaurs appeared about 230 million years ago. Modern humans have existed for perhaps 300,000 years. All of human recorded history spans roughly 10,000 years. 1 billion years contains 100,000 complete spans of recorded human history. The continents have moved substantially in 1 billion years. Life has evolved beyond recognition. 1 billion years is a very long time by any human standard. Now multiply by 100. 100 billion years is roughly the expected remaining lifespan of the universe in the Big Rip scenario, with a moderately phantom dark energy equation of state. The Sun will be long dead by then. The Milky Way will have merged with Andromeda and dozens of smaller galaxies into a single amorphous elliptical structure. The universe's large-scale structure will look completely different from what we observe today, 100 billion years. Now consider 100 trillion years, the approximate time until the last red dwarf stars exhaust their fuel and the universe enters the degenerate era. 100 trillion is 100 billion times 1,000. At this point, the universe will have lived for roughly 7,000 times its current age. Every star-forming molecular cloud in every galaxy that exists today will have long since been exhausted. The raw material for new star formation will be gone. The only lights will be the fading embers of white dwarfs, slowly cooling over timescales comparable to, or longer than, the time the universe has already existed. Then consider 10 to the 40th power years, the estimated timescale for proton decay if it occurs. This number contains so many digits that writing it out in full would not add comprehension. The current age of the universe is 13.8 billion years. 10 to the 40th power is roughly 10 to the 31st power times the current age. If you wrote the current age of the universe as a single atom, 10 to the 40th power of those atoms laid end to end would span a distance larger than the observable universe. These numbers do not fit in the mind. They exist as labels on a timeline that extends so far beyond human experience that the concept of duration loses its usual meaning. And 10 to the 100th power, the estimated time for the last supermassive black hole to evaporate through Hawking radiation, is 10 to the 60th power times longer than 10 to the 40th power. The entire degenerate era, with all its slowly cooling white dwarfs and neutron stars, occupies a vanishingly small fraction of the timeline to the universe's final black hole evaporation. Why does any of this matter practically? In one sense, it does not. No human will witness any of these events. Even in the most optimistic scenarios for the long-term persistence of some form of intelligence in the universe, the challenges of sustaining any physical system for these timescales are challenges so far beyond current understanding as to be effectively fictional. But there is another sense in which these timescales matter enormously, and it has to do with understanding what the universe is. The physical laws that operate over these timescales are the same laws that govern the familiar world. The second law of thermodynamics, which says that entropy never decreases in an isolated system, is the reason the big freeze will end in maximum entropy rather than spontaneous order. Quantum mechanics, with Hawking radiation, is the reason black holes are not truly permanent. These are not exotic laws invoked only for cosmological speculation. They are the laws you encounter in everyday physics, applied to circumstances far outside everyday experience. When we trace the fate of the universe through these timescales, we are doing the same physics we do to understand how a star burns or how a nuclear reaction releases energy. The same principles, followed to their ultimate conclusions, are what these vast timescales reveal. Physics is consistent across all scales and all times. That consistency is the reason cosmologists can make credible statements about events a Google years away, not because they have special foresight, but because the laws do not change, and the laws are enough. Part 15. Dark Energy, the Higgs Field, and Why Physics is Not Finished. There is a temptation, when reviewing the history of physics, to conclude that the big picture is complete. The Standard Model of particle physics describes 3 of the 4 fundamental forces with extraordinary precision. General relativity describes gravity and the large-scale geometry of spacetime equally well. Together, these frameworks account for essentially every phenomenon we can observe in laboratory experiments and astronomical observations. But dark energy is not a marginal anomaly in an otherwise complete picture. It is the dominant component of the universe, making up 68% of the total energy content, and it is completely outside the predictive reach of the Standard Model. Quantum field theory predicts a vacuum energy that is 55 to 120 orders of magnitude too large to be dark energy. General relativity can accommodate it as a cosmological constant, but cannot derive its value. This is not a case where the existing frameworks need modest refinement. Something fundamental is missing. The cosmological constant problem has a parallel in the mass of the Higgs boson. When the Large Hadron Collider at CERN discovered the Higgs boson in 2012 at a mass of 125 giga-electronvolts, the measurement placed the Standard Model in an interesting situation. The Higgs mass was not predicted by the theory, it was measured, and the measured value falls in a range that makes the vacuum metastable, meaning the current state of the vacuum might not be the true ground state of quantum fields. There is potentially a lower energy state separated from the current vacuum by a quantum barrier. The universe may be sitting on a hillside rather than at the bottom of a valley, and quantum tunneling could eventually initiate a transition to the true ground state, creating a bubble of different physics that would expand at the speed of light. If this vacuum decay occurs, it would not be a gradual change. There would be no warning. A bubble of the new vacuum would nucleate at some random point in space, from a quantum fluctuation, and it would expand outward at the speed of light. Within that bubble, the properties of all particles and forces would be different. The masses of particles, the strengths of interactions, the structure of atoms and molecules, all would be governed by the new physics of the true vacuum. The bubble wall would approach any given location at light speed, so no information could precede it. The expansion of the universe means that the most distant parts of the observable universe would be converted before any signal from their conversion could reach us. If such a bubble had already nucleated somewhere in our observable universe and was expanding toward us, we would have absolutely no way to know. The probability of this occurring in the next few billion years, under the current best estimates of the Standard Model parameters, is extremely small, many orders of magnitude lower than 1 in the current age of the universe. But it is not 0, and over truly vast timescales, even very small probabilities eventually become near certainties. If the universe persists long enough, vacuum decay might be another way the story ends. Not through the gradual entropy increase of the Big Freeze, not through the catastrophic acceleration of the Big Rip, not through the gravitational collapse of the Big Crunch, but through a sudden and complete rewriting of the laws of physics across the observable universe. Physics is not finished. The universe is still producing phenomena that our best theories cannot fully account for. Dark energy is the most consequential of those phenomena. The vacuum stability question is another. The Hubble tension may be a third. The nature of dark matter, which dominates the gravitational scaffolding of the universe but has resisted direct detection for decades, is a fourth. These are not loose ends waiting to be tied off in the theoretical framework we already have. They are indications that the framework itself is incomplete, that there is physics beyond the standard model and possibly beyond general relativity that remains to be discovered. That new physics, when we find it, will not just explain the cosmological constant or resolve the Hubble tension. It will likely have consequences for the ultimate fate of the universe that we cannot currently anticipate. The history of physics is full of cases where solving one problem revealed completely unexpected implications. Maxwell's equations for electromagnetism led to special relativity. Special relativity led to the prediction of antimatter. Quantum mechanics led to Hawking radiation. The connections between seemingly separate problems, when pursued rigorously, have a way of revealing that they are aspects of a single deeper structure. The question of when the universe will stop expanding is connected to the question of what dark energy is, which is connected to the question of what the quantum vacuum is, which is connected to the deepest questions about the structure of space-time itself. It is not an isolated puzzle, but a thread that, when pulled, unravels into the most fundamental questions physics knows how to ask. We do not yet have the answers, but we have better tools than any previous generation for pursuing them, and the universe is still generous enough with its light to let us look. If you made it this far, genuinely thank you. This video covered a lot of ground, and the fact that you stayed with it says something. If you found it worth your time, a like or a subscribe helps this channel reach more people who spend their evenings staring at the sky and wondering what it all means. Drop a comment below with where you are in the world and what time it is as you watch this, and let us know which ending you think the universe has waiting for it. We will be back with more. Part 16. What it means to be here at this moment. Somewhere in the story of cosmic expansion, between the mathematics of Friedmann equations and the observational campaigns of Desi and Euclid and Roman, there is a human dimension that is easy to lose sight of when the numbers get large enough. The question of when the universe will stop expanding is not just a technical question about an equation of state parameter. It is the most fundamental question you can ask about the object you were born into. It is the last chapter of the only story there is. Consider for a moment what it means to be asking this question at all. The universe is approximately 13.8 billion years old. For the first roughly 400 million years, there were no stars, only cooling hydrogen and helium gas, slowly condensing under gravity. For the next several billion years, stars formed and burned and died, scattering heavier elements into the gas clouds, from which new stars, and eventually planets formed. The Earth formed 4.5 billion years ago. Life appeared on Earth within a billion years of the planet's formation. For roughly 4 billion years, life evolved in forms that had no capacity for abstract thought, no language, no cosmology, no questions about the nature of the universe they inhabited. Then, in the last few hundreds of thousands of years, something happened in one lineage, on one planet, orbiting one star among 400 billion stars, in one galaxy among 2 trillion galaxies in the observable universe. A species developed the capacity to ask questions about the universe as a whole. Not just questions about survival, about food and territory and mates. Questions about the nature of time and space and energy. Questions about why the sky is dark at night, and why distant galaxies are moving away, and what will happen in 1 trillion years. Questions that have no immediate survival value. Questions that can only be asked by creatures with enough surplus cognitive capacity to think beyond the immediate demands of existence. The universe, for the first 13.8 billion years of its existence, did not know it was expanding. It did not know what dark energy was, or that the expansion was accelerating. It had no awareness of the Hubble constant or the baryon acoustic oscillation scale, or the equation of state parameter. These are concepts that exist only in the minds of creatures capable of abstract thought, creatures whose physical substrate is made of the same atoms and the same dark matter and the same forces as everything else in the universe, but who have organized themselves into structures capable of modeling the whole from within. When astronomers at the Kitt Peak Observatory point the Mayall telescope at a distant galaxy and measure its spectrum, they are doing something that no physical process in the universe does automatically. They are measuring, reasoning, constructing models, testing predictions against data, revising understanding, and gradually converging on truth. The universe does not care about this process in any anthropomorphic sense, but the process is happening inside the universe, using the universe's own components, and it is producing genuine knowledge about the universe that would otherwise exist nowhere. There is something worth pausing on in the specifics of the dark energy discovery. In 1998, two teams of astronomers, totaling several hundred scientists between them, were looking at Type 1a supernovae in distant galaxies. They expected to find that the expansion was decelerating, and they were measuring how much. Both teams found the opposite. The data did not fit their prior expectations. They checked their instruments, their calibration, their analysis pipelines. They considered systematic errors. They disagreed with each other about various technical details, and eventually, reluctantly in some cases, they accepted what the data was telling them. The universe was not doing what they thought it was doing. Something was pushing space apart against gravity. They did not know what. They still do not know what. But they trusted the data over their assumptions. This is what science looks like from the inside. Not a triumphant march from ignorance to understanding, but a messy, contested, self-correcting process where the data ultimately forces revision of even the most comfortable assumptions. The discovery of dark energy was uncomfortable. It introduced a problem, the cosmological constant problem, so severe that it has not been resolved in the quarter century since the discovery. It made the universe substantially more mysterious than it appeared to be in 1997, and yet the cosmologists who found it published their results, shared them with the community, and accepted the Nobel Prize for a discovery that made their field harder, not easier. This is worth remembering when the open questions feel frustrating. We do not know what dark energy is. We do not know whether the expansion will continue forever, reverse, or tear the universe apart. The DESI results hint at something unexpected about the behavior of dark energy, and those hints have not yet resolved into a clear picture. The Hubble tension remains stubbornly unresolved. The vacuum stability question hangs open. These are genuine uncertainties, and some of them may remain unresolved for decades. But each of these uncertainties is a specific, testable question. The equation of state parameter can be measured more precisely with more data. The Hubble tension can be constrained further with new distance measurement techniques and gravitational wave standard sirens. The vacuum stability depends on measurements of the Higgs boson mass and top quark mass that particle physics is continuing to refine. These are not questions that are in principle beyond the reach of observation. They are questions that are currently being pursued with the best instruments our civilization can build, and the answers are becoming clearer with every passing year of data collection. In the early 1920s, astronomers did not know whether the spiral nebulae were gas clouds within the Milky Way or entire separate galaxies. The question was unresolved, and the evidence was ambiguous. Then Hubble measured the distance to the Andromeda Nebula using Cepheid variables, and the ambiguity was gone. The nebulae were galaxies. The universe was vastly larger than anyone had imagined. A specific observational program resolved a specific question, and the knowledge gained was permanent. The same thing will happen with dark energy. Not immediately, and not without further surprises along the way. But the observational programs now underway, the accumulated precision of millions of galaxy spectra from DESI, the billions of galaxy-shape measurements from Euclid and Roman, the supernovae from Rubin, the gravitational wave standard sirens from LISA, will eventually narrow the possibilities to the point where the question of dark energy's nature and behavior has a definite answer, or at least a definite range of possible answers distinguishable from each other by future observations. When that happens, the question of when the universe will stop expanding will have an answer. Not a comfortable one, perhaps. The Big Freeze offers nothing for intelligence to hope for except a very long time before the end. The Big Rip offers only 20 or 30 billion years, barely more than the current age. The Big Crunch offers a different kind of ending, possibly followed by a new beginning that has no memory of ours. None of these is a comforting destination, but all of them are comprehensible. All of them follow from the physics we understand. All of them are, in the deepest sense, scientific answers to a scientific question. And perhaps there is something in that fact that is more than just consolation. The universe is not only vast, not only ancient, not only expanding, not only filled with dark energy whose nature we cannot yet explain. It is also legible. Its behavior follows rules, written in the mathematics of quantum fields and curved space-time, that minds evolved from stardust on a small rock can actually work out. Not completely, not yet, not without gaps and uncertainties, but substantially. Enough to trace the history of 13.8 billion years of cosmic evolution and project forward into the trillions and quadrillions of years to come. The universe will not stop until it is ready to, or until the physics forces it to, or until something we have not yet thought of changes the picture entirely. But in the meantime, we are here, looking up at a sky full of ancient light, building the instruments and the mathematics and the community of knowledge to figure out what comes next. That is not a small thing. It is, perhaps, one of the most remarkable things that has ever happened in 13.8 billion years of cosmic history. Thank you for spending this time with these ideas. If this video found you somewhere quiet and curious, leave a like and subscribe to come back for the next one. Drop a comment below with your location and the time you're watching, and tell us which ending you think is waiting at the end of the universe. We read them all, and the conversations in the comments are genuinely some of the best discussions these videos produce. See you in the next one. Part 17. The Cosmic Microwave Background and the Memory of Fire. Everything we know about the early universe, and therefore everything we can extrapolate about its future, rests on our ability to read a faint whisper of radiation that fills the sky from every direction. The cosmic microwave background, the CMB, is the oldest light in the universe. It was emitted approximately 380,000 years after the Big Bang, when the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms for the first time, releasing radiation that had been trapped in the hot plasma and allowing it to travel freely for the first time. That radiation has been traveling ever since. It has been stretched by the expansion of the universe from the optical and near-infrared wavelengths it had when it was first emitted to the microwave wavelengths it has today, corresponding to a temperature of just 2.725 degrees above absolute zero, colder than the coldest place on Earth by several hundred degrees. When you look at a map of the cosmic microwave background, what you are seeing is a snapshot of the universe as it appeared 380,000 years after its birth, imprinted on a sphere surrounding us at a distance of about 46 billion light-years. That snapshot is not uniform. It has tiny temperature variations, hot spots and cold spots, at the level of 1 part in 100,000. These variations are the seeds of all the structure in the universe. They represent the slight density fluctuations in the early plasma, regions where the matter was slightly denser and slightly hotter, and regions where it was slightly less dense and slightly cooler. Gravity amplified these fluctuations over billions of years, causing the denser regions to collapse into galaxies and galaxy clusters, and the less dense regions to expand into the vast cosmic voids that occupy most of the universe's volume today. The pattern of these temperature fluctuations is not random. It has a specific, predictable power spectrum, a distribution of fluctuation sizes determined by the physics of the early plasma and the initial conditions set by inflation. By measuring this power spectrum with precision, cosmologists can determine the composition of the universe with extraordinary accuracy. The relative heights of the peaks in the power spectrum tell you the density of ordinary matter, the density of dark matter, the geometry of the universe, and, crucially, the dark energy density. The CMB essentially tells you the recipe for the universe at the time of its earliest light. The Planck satellite, operated by the European Space Agency, and producing its final results in 2018 and 2019, provided the most precise map of the CMB ever made. Its measurements determined the key cosmological parameters to precisions of a percent or better. The universe is 13.8 billion years old. It is flat to within 0.5%. Ordinary matter makes up 4.9% of the total energy content. Dark matter makes up 26.8%. Dark energy makes up 68.3%. The Hubble constant, from the Planck analysis, is 67.4 kilometers per second per megaparsec. These are numbers that will not change substantially, because they are derived from the physics of the early universe. The CMB is a record that cannot be altered by anything that happens later. The temperature fluctuations it carries were set in the first fraction of a second and then frozen in place. They encode the fundamental parameters of the cosmological model in a way that is independent of what dark energy does after the recombination epoch. But they do depend critically on one thing: the model used to interpret them. The Planck team uses the standard LCDM model, meaning the lambda cold dark matter model, which assumes dark energy as a cosmological constant, to translate the observed temperature fluctuations into parameter estimates. If dark energy is not a cosmological constant, if it has been evolving over the history of the universe, then the model used to interpret the CMB fluctuations needs to account for that evolution, and the derived parameter values, including the Hubble constant, might shift. This is one of the reasons the Hubble tension is so conceptually important. The Planck CMB measurements and the local distance ladder measurements are not just two independent measurements of the same thing. They are measurements that probe different epochs of cosmic history, connected through a model. If the model is wrong in a way that affects the early universe epoch, the CMB-derived Hubble constant would be wrong, even though the CMB measurements themselves are perfectly accurate, and the local distance ladder measurements would be right. This is precisely what many theorists exploring the Hubble tension expect, which is why so much theoretical work has gone into modifying the physics of the early universe epoch, between the time the CMB was emitted and the present, in ways that would shift the Planck prediction upward toward the local measurement value. The proposed modifications to early universe physics are varied. Early dark energy models suppose that there was a brief episode of additional dark energy density before recombination that changed the sound horizon, the distance that sound waves traveled in the early plasma before recombination, which is one of the key scales that translates into the CMB peak positions and the baryon acoustic oscillation scale. Other proposals involve modifications to the Hubble parameter itself in the early universe, additional light particle species that change the expansion rate before recombination, or modifications to general relativity that alter the growth of structure between the CMB epoch and today. None of these proposals has yet achieved consensus or provided a perfect fit to all available data simultaneously. The Hubble tension may yet turn out to be a systematic error in one of the measurement methods, but if it persists as more data accumulates, the eventual resolution will tell us something important about physics in the epoch between the CMB and today. Physics that we are currently assuming follows the simple LCDM model, but that might not. The CMB will remain a resource for cosmology for as long as we can measure it. Its temperature fluctuations encode the initial conditions of the universe in a way that subsequent observations can never replicate. Future CMB experiments will push precision further, mapping the polarization of the CMB to even finer scales, looking for signatures of primordial gravitational waves from inflation, and constraining the physics of the early universe to degrees that the Planck satellite could not achieve. The CMB is not a completed chapter. It is an ongoing laboratory for fundamental physics, one whose subject matter is the universe in its earliest accessible state, and whose results constrain everything from the nature of inflation to the equation of state of dark energy to the ultimate fate of the cosmos. Understanding the fate of the universe requires understanding its origin. The two are connected through the physics of everything in between, and that physics is what the next generation of instruments, and the generation after that, and the generation after that, will continue to probe. The question is alive, the answer is approaching. The universe, for all its indifference to the beings who live inside it, is patient enough to let the answer come. Part 18. Looking up, looking forward. It is late at night somewhere as you watch this. Maybe the sky outside is clear and you can see a few stars through the window. Or maybe it is overcast. Or maybe you are in a city where the light pollution has reduced the entire night sky to a uniform orange glow with a few of the brightest stars still visible. Whatever the sky looks like from where you are, the universe is out there, doing what it has been doing for 13.8 billion years. It is expanding. Every galaxy beyond the local group is moving away from us, red-shifting as it goes, its light stretched by the growing space between here and there. The cosmic microwave background is a hiss of cold radiation arriving from all directions, the faint echo of a hot beginning. Dark energy, whatever it is, permeates every cubic centimeter of space, pushing the expansion forward with a persistence and a pervasiveness that no instrument can directly detect, only infer from the cumulative effect it has on the distances to millions of galaxies. Right now, somewhere in Arizona, the DESI instrument is open to the night sky, its robotic fibers clicking into position to point at galaxies billions of light-years away, measuring the tiny shifts in spectral lines that record the galaxy's recession speed and distance. Every spectrum it records is a data point in the history of cosmic expansion. Every data point narrows the constraints on the equation of state parameter of dark energy. Every narrow of those constraints brings the ultimate fate of the universe into slightly sharper focus. The scientists doing this work are not dwelling on the cosmic scale of what they are measuring. They are debugging software, calibrating instruments, writing code to reduce and analyze data, arguing about systematics in journal papers, drinking coffee at 3 a.m. at the telescope, going home and coming back and checking the results again. The work of science is mostly the work of checking, of being wrong and figuring out why, and being less wrong and checking again. The grand question of the universe's fate is addressed in small increments, through thousands of careful measurements and careful analyses, each adding a small amount of information to the accumulated total. This is how knowledge grows, not in revelations but in accumulations, not in single decisive experiments, but in the convergence of many independent lines of evidence toward a consistent picture. The picture of cosmic expansion, from Hubble's initial observations to the current state of DESI and Euclid and the ongoing Hubble tension debate, has been built up over nearly a century of careful, contested, incremental measurement, and it is not finished. The question that began this entire journey, when will the universe stop expanding, does not yet have a definitive answer. The answer depends on the nature of dark energy, which we have measured the effects of, but not identified the cause of. It depends on whether the DESI hints of evolving dark energy are confirmed by future data. It depends on whether the Hubble tension points to new physics that modifies the expansion history in the early universe. It depends on whether the vacuum is stable, whether protons decay, whether black holes truly evaporate as Hawking's calculation predicts. All of these things are being investigated. All of them are moving toward resolution, some faster than others, some in directions that are surprising us. The surprise is itself informative. It means the universe is not simply confirming our prior expectations. It is still telling us things we did not know. Maybe it never stops expanding. Maybe it expands forever into cold darkness, and the only ending is the quiet, asymptotic heat death of maximum entropy and perfect stillness. Maybe dark energy weakens and reverses, and the expansion decelerates over billions of years, halts and reverses, and everything falls back together into the heat and density and incomprehensible compression of a final singularity. Maybe phantom energy tears the universe apart, atom by atom, nucleus by nucleus, in a terminal escalation that makes even the heat death seem gentle by comparison. Or maybe something we have not yet thought of. Maybe the Hubble tension, when resolved, will point to a modification of gravity that changes the expansion history in a way none of the current scenarios anticipate. Maybe the vacuum decay, if it occurs, preempts all of these scenarios. Maybe the universe has a property we have not discovered that changes everything. The honest answer is that we do not know. And the honest response to not knowing is not to stop asking, not to pretend certainty where there is none, but to keep measuring, keep checking, keep narrowing the possibilities with every new generation of instruments. To hold the question open until the data closes it. To be the kind of creatures who look up at a sky full of ancient light and feel not just wonder, but the specific productive discomfort of a question that has not yet been answered. We are those creatures. We are doing that work. And one day, not soon by any human measure, but soon by the reckoning of a universe that has been running for 13.8 billion years, we will know. Until then, the sky is full of data, and we are still watching. If you made it here, truly, thank you. This was a long one, and it asked a lot. If you found it worth your time, a like or a subscribe costs you nothing and helps this reach more people who spend their nights thinking about these same questions. Drop a comment with your location and what time it is as you watch this. Tell us what you think. Which ending do you believe is coming? Which one keeps you up at night? We will be back.